So welcome back again. As we talked about at the first part of the week, we talked about the temperature and how we could find that from the peak wavelength from that graph. And then we said, okay, well, if we know the luminosity and we know the temperature, we can also find the size. So that's what we're going to talk about today. And again, we're going to use these same continuous spectrum graphs that we've been using before, but keep in mind that little curve that you're seeing there is just a bar graph. It's showing you how much of each color we have from that. But we're mostly interested in what the peak is of that curve right there. That's going to tell us what's going on from Wien's law for temperature. And then we're also going to use that when we're talking about how to find the peak luminosity, and then again that gives us the size. So let's get started. All right, so last time we talked about how to find the temperature. Now we're going to talk about how to find the size, and we can also get this from this same continuous spectrum, this kind of curved graph. Again, remember that this is just a bar graph. It's showing me how much of each of these colors I've got. So here I've got just a little bit of blue, here I've got a whole lot of yellow, and a little less of red, until finally down and get into this part of the infrared, and I've got almost none of all. So just as a reminder, we produce that spectrum this way. We take the light from our star, we shine it through the prism, that breaks it into the rainbow, and then we use a sensor to detect how bright, how much energy of each of these colors we're getting to measure its intensity. So the key thing here, we're talking about the Stefan-Boltzmann law, but again, think of it more as a tool. The luminosity depends upon the size of the star and the temperature of the star. And if you think about it, that kind of makes sense. We talked about this last time, how Betelgeuse and Rigel are the same brightness, even though Betelgeuse is much cooler. Well, the only way that's possible is if Betelgeuse is just really, really big. And you can kind of think about it this way. All candles burn at the same temperature because they're all just wax, and it's the vaporized wax that's causing the flame. So they're all the same temperature. If I've got one candle here, and then I've got 100 candles here, they're all at the same temperature because temperature of the wax. However, because this is so much greater surface area, it's going to end up being brighter than that one single candle. So if two objects are the same size and one's really bright, we'll do it this way, it's really bright. If they're the same size, then this one must be hotter. On the other hand, if they have the same temperature, the bigger one is going to be brighter, like the candles that we talked about. So let's see how we can get some examples of that. So here's our graph, and we've worked with this before. This is star A and star B, and you can look on your page here and you'll be able to see those. And as always, I want you to pause the video after each one and see if we can figure out how to make it work. You can even pause the video and do the whole chart if you want, but let's talk about it individually for this one. So this is our luminosity. This is showing how much of each color that we're getting. The peak wavelength right here, the peak is really the only one we're interested in. Here's the wavelength, and here's the luminosity for that point. That's what we're looking at. So between star A and star B, which one has the higher temperature? Think back to what we covered in the last video. Pause the video and make your choice. All right, so star A is peaking down here in the blue. Yeah, I know it's violet, but there's only two colors, right? Blue and red. Whereas star B is peaking here in the red. Hotter objects are bluer. Therefore, star A must be hotter. Wien's law. Always remember, Wien's law. Hotter objects are bluer. I should be able to call you up at 2 o'clock in the morning and say, hey, why are hotter objects bluer? And you can say, Wien's law, please stop calling me, all right? So star A must have the higher temperature. Now, which has the greater energy output? For energy output, we're talking about luminosity. Which one peaks and is putting out more luminosity? Pause the video, make your choice. Well, most students get this pretty readily. Star A is obviously peaking up here, so it's got the higher luminosity. What you don't want to do is to think that just because star A is taller means it's hotter. That's not true. In fact, I could have a star that peaks way over here, and it's going to be red, so it's going to be cooler. It's just very, very bright, okay? So when we're trying to figure out then which one must be hotter and which one must be cooler then, this one is brighter and it's hotter, right? Whereas star B is cooler and it's dimmer. So let's review our first two before we get to this new one. So the first one, star A, is definitely going to be the hotter. And then star A also has a greater energy output. Now, pause the video. Which one do you think is going to be bigger, or are they going to be the same size? Well, in this case, they're the same size. Think about that. Just because this is bright, not because it's bigger, but just because it's hotter. That's it. These stars are basically the same size, and so therefore it's going to be brighter just because it's hotter. Think about that. Okay, so this is brighter, it's hotter, but I want you to think of it the other way around. It's brighter because it's bigger. I'm sorry, because it's hotter. I said that backwards. It's going to be hotter, so therefore it's got to be the same size as star B right here. Okay, so you're back. Now we talked about star A is a higher temperature. Star A is also has the greater energy output. Which one of these is bigger, or are they the same size? Well, they're actually the same size, and that might have been challenging for some of you. But think about it. This is bright only because it's hot, not because it's big. And so that tells us that this must be the same size as this one. This one is dim, not because of its size, just because it's not very hot. So these two are must be the same size. Let's get some more practice and see what you can see. So here's a similar situation. We saw actually this graph last time. So here's star A here, here's star C. So star A is the same one that we were looking at before. So now we're comparing it to a star C. So pause the video. Which one has the higher temperature and which one has the greater energy output? Do both of those before unpausing the video. Back? Okay, so which one has the higher temperature? Well, star A and star C peak at exactly the same point. Well, if they've got the same peak wavelength, they've got to have the same temperature. You see why? Because hotter objects are bluer, but these two are the same color. Wavelength is color. All right, so which one has the greater energy output? Now we're looking on this scale here. Star A goes here, star C goes here, so star A must have the greater energy output. See how that works. All right, now here's the new part. Which one is larger in size? Star A, star C, or do they have the same energy output? Think about comparing the brightness versus the temperature. Pause the video, see if you can figure it out. All right, so star A is brighter than star C, yet they have the same temperature. The only way that's possible is if star A is much bigger than star C. Do you see that? So this is the example we gave with the candle. I've got one candle or I've got 100 candles. They're the same temperature, but that 100 candles is going to be brighter just because it's bigger. It's got a bigger surface area from here. So these two stars are the same temperature, but star A is brighter. It's got a greater energy output because it's a bigger star. All right, look at the next one. And you've seen this graph before, so hopefully you remember what the answer is, but let's see if we can work it out. So once again, this time I want you to do all three. So pause the video and do all three of these before we come back. Do that now. All right, so star A is here, star D is here. Which one has the higher temperature? Well, to figure out temperature, we're using the wavelength down here. Shorter wavelengths, bluer wavelengths are going to be hotter. Star A peaks in the blue, star D peaks in the red. Hotter objects are bluer, so therefore star A must be the hotter object. Now when we're looking at energy output, we're looking at the luminosity. Both of them come right here. Star A has this luminosity, star D has this luminosity. So they're the same energy output because they both reach the same height here. Now comes the trickier one. Which one must be larger in size? Well, star A is hotter than star D, yet star D is just as bright. So this is Betelgeuse and Rigel. So star D would be equivalent to being Betelgeuse. It's red, but it's still very, very bright. Whereas star A, which is kind of like Rigel, is blue and is also very bright. So the only way, if star D is cooler, the only way it's possible for that to work would be if star D were actually larger. It must be much larger than star A. Okay. So let's bring our camera down here. So here's Betelgeuse, here's Rigel. You tell me, which star is the hottest? Rigel must be the hottest because it's bluest. Which star must be coolest? Now, okay, you probably figured that out. Betelgeuse must be the coolest, but that's because it's reddest. Good. Now, which one is brightest? Well, they're very close to being the same brightness. Do you see that? So this is the same situation that we had here. Star A is hotter because it's bluer. Star D is cooler because it's redder. However, they're the same brightness. So which star must be larger? Which must be smallest? Betelgeuse must be larger because it's cooler. The only way it can be that bright must mean that it is, oh my God, huge. And in fact, Betelgeuse is so big that if we put it where our sun is, the surface of the star would be out past the orbit of Mars. So Mercury, Venus, Earth, and Mars would all be inside the star. That's how big this thing is. It's not terribly hot, really. It's just so big. Rigel, on the other hand, then must be the smallest from that. Because it's blue, it's the same brightness as this, so it must be smaller than that. Moving the video back. Okay, so now look on the back side of your page. So a lot of times we want to show more than one star on the same graph. And yeah, I could show all these curves like we did here. With 2, it's not bad. But what happens when you've got 4 like we do here, or 1,000 stars? You're going to have all these curves and all these lines, and you're not going to be able to follow it. So most of the time we just plot just the position of the peak. And if you visualize that, this is star A. You see that? Comes up, peaks right here, and then comes down. Star C, remember, was the same temperature. It came up, peaked, and came down. Star D, the one that we just did, the Betelgeuse-like one, came up, peaked, and then came back down. And then that first one, the really cool star that we did, was star B that went like this. So looking at your graph then, we want you to label where would the hottest stars be found. And remember that hot is down here. If the temperature is showing you down here. So the hottest stars are going to be the bluest stars. So all of this area, not just down here, but also up here, everywhere in here are going to be the hottest stars. The coolest stars are going to be right here. So where are the brightest stars going to be found? Well, that's these up here, right? So anything up here. So A and D are the same brightness because we can read that off here. And then down here are going to be the dimmest stars. Now look on your worksheet, it says show where the smallest stars are found. Well, if you remember, we said that that C was smaller than A, and A was smaller than D. Remember that? So between star A and star C, they're the same temperature, so we said star C must be smaller than star A. However, between star A and star D, they're the same brightness, but D is cooler, so it must be bigger. So if we're going to rank these, then this becomes the biggest, this is the next biggest, and this is the next biggest. So the smaller stars are down here. And it turns out that if I draw lines going down diagonally like this, those are lines of constant size. So it says circle the only 2 stars that could be the same size. Well, those are the ones that lie on that diagonal line. So star A and star B must be the same size. And go all the way back to the first slide, the first problem we compared. Now you should be able to see why star A and star B are the same. Okay. So drawing an arrow then from the smallest stars to the largest, that's going to go this way. That's from the smallest stars to the largest. So this way would be small, this would be large. Remember, don't get confused. When I was talking about those diagonal lines, those are ones that are the same, but it increases from here all the way up to here. So each one of those lines, each one of those diagonal lines would be a larger and larger star. All right, so here's the tool that we use for actually calculating it when I need it. R is measured in solar radii, so don't get too confused by that. It's just like solar looms. So if I have 1 solar radii, it's the same radius as the sun. If it's 2 solar radii, it's twice the radius of the sun. If it's half a solar radii, it's half the radius of the sun. So L here has to be the luminosity in solar looms. So 1.5, whatever it is. You're raising it to the 0.5 power. Some of you know that that's the same thing as taking the square root. If you want to do that, that's fine. It's also perfectly fine to do 1.5 and then hit your caret or y to the x or whatever it is, raised to the 0.5, and then that will give you the same value there. T then must be measured in Kelvin. Now, don't get confused. You got to do T divided by 5800 first, then square it. So don't just square the T. So the parenthesis means you have to do that first. What I often suggest students do is work out the top, write it down. Work out the bottom, write it down. then divide it. If you do that, you'll almost never make a mistake with parentheses. But I know you all want to put it in at the same time. Just be real careful. There's an implied parenthesis of everything in the top and then everything in the bottom. So do your L raised to the 0.5. If you've got one of those fraction buttons, that's fine. But then parenthesis t over 5800, close, squared. Oh, and then we ask, is it directly or inversely proportional? So what we're talking about here, the temperature and the radius, are they directly or are they inversely proportional? Well, one's in the top and one's in the bottom. So they're inversely proportional. So that means, let's see if that makes sense. As the temperature goes down, the radius must be going up if the luminosity is the same. That's our case with Betelgeuse and Rigel. The temperature, the luminosities were the same. Betelgeuse had a lower temperature, T went down, so that means R must go up. So this is exactly what we found just by using logic. And you can do this, that kind of comparison using the equation, even if you don't want to do any math. You don't have to logic through the graph and all that if you don't want to. Just come over to here, you know how to use the thumbs up and thumbs down, and say, okay, Betelgeuse has a lower temperature, that goes down, they're inversely proportional, so the radius must go up. It must be the bigger one. Now, looking at radius and luminosity, are they directly proportional or are they inversely proportional? Well, they're both on the top, so they're directly proportional. They either both go up or they both go down. So let's suppose I've got two stars that are the same temperature. That would be like our star A and star C. They're the same temperature. Star A has a higher luminosity, therefore it must have the higher radius because they go up together. And that's what we found. Okay? If you're not sure about that, go back to the worksheet, have this formula down there beside you, and work it out. You can copy that formula down onto the page. I'll almost never ask you to do a calculation where you're finding the size of the star. Occasionally, you may have to do that sometimes, but it's more important that you be able to use these arrows to figure out what to do. All right? All right, so we've talked about temperature in the last one. This tool for this time is size. So this is what we're using to find out the size. And again, we get that from the continuous spectrum. The Stefan-Boltzmann law, you have to first find the temperature and the luminosity. Find that temperature, find the luminosity, plug it in, and then you can get the radius and solar lumens for that. That's if you need the numbers. Sometimes, and you do sometimes, but sometimes we can get by with just doing our thumbs up and thumbs down, and we're good to go. Okay, so that's it for this time. So we get a lot of information out of the continuous spectrum, out of that rainbow curve that we were talking about there. We get the temperature, we get if we've also got the luminosity, then we can find the size. Now, if I needed a number, remember, I might just give you the flux and the parallax. From that, then you could get the luminosity, right? If I also gave you the peak wavelength, you could then get the temperature. If you know the luminosity and you know the temperature, now you can get the size. So you see how we can take each of these tools and put them together, and that gives us even more information out of it. This is why it's so important that you really understand each tool as we go along. And if you feel like you're starting to flounder a little bit, feel like you're starting to get a little behind, go back to some of the earlier lessons and review it and make sure that you've got those fundamental tools, because we're going to be building on that from here on out. All right, that's it for this time. We'll see you next time.